Good evening to one and all. This is Dr. Vijay Kumar, working as an assistant professor in the Department of Mechanical Engineering from St. Peter's Engineering College, Hyderabad. Today, we'll solve the problems from the gas turbines. Already we discussed what are the classifications of gas turbine, what are the differences between the open type, closed type gas turbines, then how the improve the efficiency of the gas turbine. From the efficiency improvement methods to improve the efficiency of the gas turbine, the methods are: first one, intercooling between the multi-stage compressors, and second one, reheating, and third one, regenerate. Now, let us today we solve the intercooling. With the help of the intercooling, how much of efficiency will be increases. Let us take one example problem. A gas turbine plant consists of two-stage compressor with perfect intercooler and a single-stage turbine. If the plant works between the temperature limits of 300 Kelvin and 1000 Kelvin and 1 bar and 16 bar, find the net power of the plant per kg of air. Take specific heat at constant pressure as 1 kilojoules per kg Kelvin. This is the data. So for any problem, first note down the given data. What he has given? He has given a gas turbine plant consists of two-stage compressor. So it is related to multi-stage compressor with intercooler. So it is the one of the modified gas turbine for improving the efficiency of the gas turbine. So what are the temperatures limit he has given? So initial 300 Kelvin and 1000 Kelvin. So temperature initial. So first draw the TS diagram. First we have to draw the TS diagram of multi-stage compressor with intercooler. So for intercooler, is it closed cycle or open cycle? He didn't mention the open cycle or closed cycle. Let's see. A gas turbine plant consists of two-stage compressor with a perfect intercooler and a single stage. So he didn't mention is it open cycle or closed cycle. So assume it is a closed cycle. So if it is closed cycle, it is a continuation line. If it is open cycle, so this is the dotted line. Now assume it is a it is a 1, 2, 3, 4, 6. So here T4 equal to T6, T1 equals to T5, direction it is these are the direction. So 1 to 2 is the heat addition at constant pressure, and 2 to 3 is the isentropic expansion, and 3 to 4 is the heat rejection, and 4 to 5 is the isentropic compression, and 5 to 6 again heat rejection, and 6 to 1 is the isentropic compression. So here 4 to 5 and 6 to 1 is the isentropic compression, and 2 to 2 is the isentropic expansion, and 1 to 2 is the heat addition, and 3 to 4 and 5 to 6 is the heat rejection at constant pressure. So these are what he has given. He has given the initial temperatures between 300 to, so T6 equals T4 equals to 300 Kelvin, and T1 equals to T2 equals to, not T1, so T2. Final temperature is the 1000 Kelvin. So initial temperature and final temperature. He has given the two temperature limit, and P1 pressure here, P1 equals to P2, P5 equals to P6, P3 equals to P4. Here the pressure constant. So P1 equals to 16 bar, and P6 equals to 1 bar. Okay. Now we have to find out the perfect intercooler. So for calculating, if it is perfect intercooler, for calculating the either P5, sorry, it is a P4, it is P4. P4 is the 1 bar, it is the 1 bar, and this is the 16 bar pressure. Now for calculating the inter means in the middle pressure, we have to calculate first. For calculating the perfect, when it is a perfect intercooler, when it is a perfect intercooler, now P6 equals to P5 is equals to square root of P1 into P4, or we can write square root of P2 into P3. P2 into P3. Either any one relation we have to calculate the pressure. So what is the P1? 16 bar. So it is equals to square root of 16 into 1. So 16 into 1, 16. Square root of 16 is equals to 4 bar. So it's the temperature and entropy diagram. So now intercooler is 4 bar. Now what we have to find out? We have to find out the net power developed by the plant. For calculating the net power developed by the plant, we have to calculate the turbine work as well as compressors work. Compressors work, we have to, the difference between the turbine work and compressor work is the net work done, developed by the gas turbine. So for calculating the turbine work and compressor work, we need the temperatures. We know the T6 and T4, but we don't know the T1, as well as we know the T2, but we don't know the T3 temperature. Now we have to calculate T1 and T3, and as well as T5 also for calculating the compressors. So we know that isentropic process 2 to 3. We know that isentropic process 2 to 3 T3 by T2 equals to P3 by P2 power of gamma minus 1 by gamma. Already we did last class we derived it. So equal to, what is the P3? P3 is the 1 bar, P2 is the 16 bar. So 1 by 16 power of, what is the gamma value? 1.4. 1.4 minus 1 by 1.4. What is the value? With the help of calculator, you have to calculate the, so T3 by T2 1 by 16, after calculation I got 0.453. Therefore we know the maximum temperature. So T3 equals to 1000 into 0.453. What is the value? So 1000 into 453. So 453 Kelvin. Directly we can write it. Similarly, for isentropic process at 4 to 5. Isentropic process 4 to 5. T4 by T5 is equals to P4 by P5 whole power of gamma minus 1 by gamma. Now P4 equals to 1 bar, P5 equals to 4 bar. So 1 by 4 all to the power of 1.4 minus 1 by 1.4. So 1 by 4 is the 0.5 all to the power of this one. So after calculator, so I got 0.673. So we need calculate the temperature point at 5. So T5 equals to T4 divided by 0.673. So what is the T4? Temperature at 4 is the 300. 300 divided by 0.673. After calculation I got 446 Kelvin. Now similarly, isentropic process at 6 to 1. Or else we know that for perfect intercooling, T1 equals to T5. Already we calculated the T5. So it is equal to T1 only. So that is for perfect intercooling. Already mentioned with the perfect intercooler. So T5 equals to T1. So whatever the requirement, we got the corresponding values. Now calculate the work done by the turbine per kg of air. So for calculating turbine work, what is the formula? So to isentropic expansion 2 to 3. So formula is the Cp into T2 minus T3. What is the T2 value? Cp value is already as given 1 kilojoules per kg Kelvin. So 1 into 1000 minus, what's the T3 value? T3 453 Kelvin. 453 Kelvin. So answer is after calculation 1000 minus 453, so it is 547 kilojoules per second. So we have calculated work done per kg of air. And now next, similarly, work done by the compressor per kg of air. So formula is, so what is the compressor work? 6 to 1 as well as 4 to 5. So Cp into T1 minus T6 plus T5 minus T4. This is the compressor one. So temperature T1 is the T5 value, so that is 446 Kelvin. So Cp equals to 446 minus 300 plus 446 minus 300. So after calculation I got 292 kilojoules per second. 146 plus 146, so it is 292 kilojoules per second. Now we know that work done by the plant per kg of air, so that is nothing but total work done. So is the difference between the turbine work minus compressor work. So that is 547 minus 292 is equal to 255 kilojoules per second. So what we have to find out? We have to find the net power of the plant per kg of air. So total power equals to, therefore power 255 kilowatts. 255 kilowatts. This is the answer. So thank you one and all. Next class we will discuss the, now today we completed the intercooler problem, and one more problem I will discuss in the next video. So if we completed the next problem, we completed the 4th unit. Thank you one and all.